Hello and welcome to Common Core Geometry by eMATHinstruction. My name is Kirk Weiler and today we'll be doing Unit number 2, Lesson number 9 on the symmetries of a figure. This is the last lesson in Unit number 2. And Unit number 2 has been all about transformations and mostly concentrating on rigid body motions, right? But a transformation is really anything that will take a geometric object, whether it be a point, a line segment, an angle, or a more complicated figure like a triangle, rectangle, or square, and map it to some other figure. Symmetries, though, are very special types of transformations. So let's get into their technical definition right away. All right, now you've been studying symmetries really probably since elementary school because they're inherent in many of the figures that we look at. All right, and they're basically a way of saying, well, that figure looks kind of the same from one side as it does from the other side. But they're much deeper than that mathematically, and in fact, the application of symmetry comes up all over the place in various fields, whether it be art or chemistry, crystallography, lots of different things have symmetry in them. So let's take a look at the technical definition of what a symmetry is. Symmetries. A transformation that maps a figure onto itself, a transformation, so a symmetry is a transformation, that maps a figure onto itself, also known as carrying a figure onto itself, is known as a symmetry of the figure. So, we talk about figures having symmetry, but a symmetry itself is a transformation. Specifically a transformation that when you look at the image of the object after you've transformed it, it looks exactly the same as the original. It's in the same location, it hasn't moved, it hasn't altered at all from the pre-image to the final image. Now to see if you really understand this, let's take a look at exercise number 1. Exercise number 1. Explain why a symmetry transformation must be a rigid motion. Explain why a symmetry transformation must be a rigid motion. All right. Well, we've been talking about rigid motions for the better part of this unit. We just introduced the idea of a symmetry. But pause the video now and see if you can answer this question. Why does a symmetry or a symmetry transformation have to also be a rigid motion? All right, let's talk about it. Well, let's think about it for a second. For a symmetry, the idea is if I had some kind of figure, all right, and I applied the symmetry transformation to it, I would see exactly this again, okay? So how does that tie into a rigid motion? Let me see if I can erase this triangle. Well, let's think about this for a second. With a symmetry, the image looks identical to the original object. So, a symmetry must preserve the shape and size of the object. So, it must be a rigid motion. Right? I mean, if we take an object and we do something to it, and then we look at it and we say, well, that hasn't changed at all, then obviously the image is identical in both shape and size to the original. And we know that any transformation that preserves the shape and the size of a geometric object is a rigid motion, so symmetries must be rigid motions. Now, of course, one could easily then say, get a little confused and say, well then, rigid motions and symmetries are the same thing. But they're not, okay? Every symmetry is a rigid motion, but not every rigid motion is a symmetry. For example, translations. It's actually pretty difficult for a translation to be a rigid motion. Or, I'm sorry, it's pretty difficult for a translation is a rigid motion. It's pretty difficult for a translation to be a symmetry. Notice, it's not impossible, but it's fairly difficult. And think about this for a minute, right? If I have this triangle, all right, let me just see if I can clone it. All right, and I translate it. Well, sure, these two are identical and they're congruent, but it's not a symmetry. Because for it to be a symmetry, this should have ended up, along with that line segment, this should have ended up right on top of that, and it didn't. So the idea of a symmetry is it must be a rigid motion, but a specific type, one that maps the figure onto itself. So let's take a look at how that works. All right, exercise number 2. Given rectangle ABCD shown below, which is not also a square, answer the following questions. The diagonals of the rectangle AC and BD have been drawn and intersect at point M. Okay, great. Letter A. What is the minimum angle you could rotate ABCD about M to have it mapped on itself? Explain. Use tracing paper if needed. All right, so we know that all rotations are rigid motions. Any rotation of this rectangle is going to preserve its shape and its size. The question is, what is the minimum amount that I can rotate about point M and have the figure land back on itself? Take a moment and pause the video now and use tracing paper to experiment with this. All right, let's go through it. Now, it would be tempting to say 90 degrees, because rectangles are all full of 90-degree angles. And yet, if I take the rectangle and I rotate it 90 degrees, what I find is that's not a symmetry. Right? A symmetry would mean I would see this thing land right back on itself, and that 90-degree rotation wasn't enough. On the other hand, right, if I've got my rectangle and I rotate it 180 degrees, then the rectangle lands on itself, right? And you can really see that. A 180-degree rotation will rotate point B down to point C, and point B down to point D, and point A down to point C. So a rotation of 180 degrees. Now, just as a little bit of a side comment, notice how it says what is the minimum angle, right? And that's because we can rotate any object, literally, any object by 360 degrees around its center point, and it will get mapped back onto itself because a 360-degree rotation brings anything back to itself as long as you're rotating about some center point. All right, that's why we had to have a minimum rotation. All right, so let's take a look at B. A rotation of 180 degrees about point M is one of the symmetries of this rectangle and of all rectangles. But let's take a look at the second part of this problem. Are there any lines of symmetry? Lines of symmetry. How would you describe them? Draw them as best as you can on the diagram. For some reason that says drawn, but we're going to say draw them as best as you can on the diagram. What does it mean, lines of symmetry? Okay, a line of symmetry is a line that you can reflect the object over and it will be a symmetry. It will map onto itself. So are there any lines of symmetry? Think about this for a moment. And the answer is yes. There's two distinct lines of symmetry. One line of symmetry is a horizontal line that passes through the midpoints of sides AD and BC And another line of symmetry is one that's vertical. So the answer is yes, two lines, and I'm going to say that pass through the midpoints of the sides. Most of the time, when students have been exposed to symmetry in the past, it's been in this context. It's always been in terms of lines of symmetry. But there are lines of symmetry and there are also rotational angles of symmetry. Just as a little demonstration of one of these, if I were to take my rectangle, please, there it is, and I were to flip it left-right, you see exactly the same rectangle, right? When I did that reflection across that vertical line of symmetry, it landed back on itself because this is a rectangle, which is a very symmetric figure in terms of lines of symmetry. Let's analyze the symmetry of some additional objects. All right, exercise number 3, we've got a nice trapezoid sitting here. We'll talk more about trapezoids in coming lessons, but let's take a look at what the problem asks us to do. Exercise number 3, trapezoid RSTU is drawn below with RU congruent to ST. Line N is the perpendicular bisect of RS and UT, and M is perpendicular through, and M is perpendicular to N through L. Ooh, boy. Which of the following transformations would carry RSTU onto itself? Verify using tracing paper. And again, I just want to point out this phrasing because it's a little bit different. We've been using the terminology map. We're going to map this object somewhere else. Carry is the exact same idea as map. I like this piece of terminology. It's kind of like, okay, I grab the figure and I carry it somewhere, right? For some reason, the terminology carry an object onto itself is almost always used in the context of symmetries and not the more broad category of transformations or rigid body motions. So let's take a look at these. Let's talk about the choices, okay? Number 1, a rotation about L by 180 degrees. Well, would that work? I don't know. Let's rotate about L by 180 degrees. Oh no, definitely not. You know, it worked in the case of the rectangle, rotating 180 degrees about that center point, but not in the case of this trapezoid, so no go there. All right, how about a rotation by 90 degrees about L? Well, that would be a 90-degree rotation, and I gotta say, even though that's a cool image, I think it's even gotten worse, so definitely not. All right, how about a reflection across line N? Well, we can flip that left-right. Ooh, yeah, right, that worked. And again, it makes sense that it worked. This is kind of going back to the work that you've done in previous years, right? The trapezoid looks identical on this side of line N as it does on this side of line N, hence the term reflection, right? If there was a mirror that we put right along N, then we would see this identical picture. So in fact, the answer is choice 3, a reflection across line N. I do want to take a look at a reflection across line M, which is going to take this and flip it up. We can do that by doing a flip up, down. And again, although it gives us kind of a cool image, it's most certainly not a symmetry. All right? So far, we've primarily been looking at symmetries and been seeing symmetries in terms of these line reflections. But let's keep going on and analyze symmetries of some regular polygons. Now, let's make sure you understand what a regular polygon is. A polygon is really any figure that's enclosed by straight line segments. Okay, that's it. The simplest of which are triangles. But let's take a look at the definition of a regular polygon. A regular polygon is any polygon whose sides have all equal lengths and whose angles have all equal measures. All right? So a regular polygon is one where all the side lengths are the same, they're all the same length, and all the angles are the same. They all have the same measure. Okay? There are tons and tons of examples of regular polygons. But the two that we're going to look at today right away, in this exercise, are the ones for a regular triangle and a regular quadrilateral. We almost never call them this, so take a moment and see if you can remember what the more common names are for a regular triangle and a regular quadrilateral. Do you remember? Well, a regular triangle is an equilateral triangle. Equilateral, right? And a regular quadrilateral, that's a square. Okay? So, we'll typically just refer to them as equilateral triangles and squares, but this terminology of regular polygons is something that you've seen before, even if you haven't used that terminology. So now, let's get into analyzing the symmetries, specifically of an equilateral triangle. Because it's got a lot more than that first rectangle we had and a lot more than that trapezoid we looked at. So let's take a look at the equilateral triangle. Exercise 5. Consider the equilateral, parentheses regular, triangle shown below. Letter A. Describe the lines of symmetry of this figure. How many will it have? Draw them. I keep putting the letter N on the end of that thing. Draw them. Okay. So, play around with this. Take out your pencil, hopefully you already had it out, and try to draw on your lines of symmetry. And if you need to, take tracing paper so that you can flip across those lines to verify that they are in fact lines of symmetry. Go ahead. Okay, should we go through them? Let's do it. So, it does say, describe the lines of symmetry. How many are there? Well, there end up being 3 of them, and they look kind of like this. That wasn't very well drawn, but those are our lines of symmetry. How would you describe them? Well, first, I'm going to say there are 3 of them. And they go through a vertex, and the midpoint of the opposite side. They don't just go through the opposite side, they go through the midpoint of the opposite side. And that kind of makes sense. If we just look at the easiest one to look at, which is this vertical line of symmetry, clearly what we have is on this side and on that side, we have sort of identical right triangles. And if you flipped this image across it, right, then what would happen is it would land on itself. All right, so pretty simple. A regular triangle has 3 lines of symmetry. Not a great surprise, right, given that it's got 3 sides, although that isn't entirely the end of the story. But it is true that a regular polygon will have the same number of lines of symmetry as it does sides. So a square will have 4 lines of symmetry, a regular pentagon, 5-sided figure will have 5 lines of symmetry, etc. But now let's talk about the rotational symmetry, because that's almost the more interesting thing in this problem. Letter B. What kind of rotational symmetry does this triangle have? Discuss both the center of rotation and the angles of rotation. All right, so I want to rotate this equilateral triangle so that it lands on itself. What point should I rotate it around? And what are the angles I should rotate it around? Think about that for a moment. All right, let's talk about it. Well, first, the center of rotation, all right, maybe I'll call it letter D, is right there. Okay, so the center of rotation will actually be, whoops, where the lines of symmetry intersect. It's a good way to describe it, given that we have those lines drawn up. But what's the angle? So you can do this calculation without actually rotating the figure, but let's take a look at rotating this figure. All right, remember, I want to look at rotating point B so it goes up to point A so that it goes to point C, and point C so that it goes to point B. Here goes my rotation. Right? There we go. It's rotated on itself. So what was that angle of rotation? Well, very specifically, it was this angle. That angle right there is my angle of rotation. How do I calculate that? Well, I calculate it based on some symmetry all by itself, in the fact that that angle, this angle, and this angle are all equal. They're all equal. And when I add them all together, I get a full rotation around the circle. So if I do 360 degrees and I divide by those three angles, each one of them is 120 degrees. So that 120 isn't the only angle of rotation, but it's the minimum angle of rotation. Let me make sure that I note that. Now, math purists would say, wait a second, no, the minimum angle of rotation is 0. And I completely agree, but that's what I would call a trivial example, meaning that, yes, of course, if I rotate the object by 0 degrees, it is a symmetry because I've literally done nothing. But the minimum non-trivial angle of rotation is 120 degrees. But there are more, right? Let's go back to the diagram. Because, let me bring this back, I could rotate point B past point A all the way to point C. And that would be this rotation. That rotation, of course, being 2 of the 120s, so also a 240 degree rotation. Now I could go one more iteration. I could rotate 3 of those. But if I do one more, then I'm to a 360 degree rotation, which is fair. Again, if I rotate 360 degrees about that center point, it will definitely land on itself. But again, a little bit trivial. I think I'll write down the 360 degree rotation, all right, just to kind of finish it out, all right? So 3 lines of reflective symmetry, and at least 3 angles of rotational symmetry, although I could take that 360 at another 120 and have a 480 degree rotation. Any integer multiple of that 120 degrees will map the figure onto itself. And we're going to see that in another exercise. Coming right up. And when I mean coming right up, I mean coming right up. So in this picture, what we have is we have a regular pentagon. And the question asks, given the pentagon shown below, which of the following angles of rotation about center point O would not carry the figure onto itself? All right, what I'd like you to do is pause the video now and think about this problem a bit. See if you can find the right choice, or the wrong choice, as the case kind of is. Are you ready to go through it? Let's do it. The key to thinking about rotational symmetry of regular polygons is finding that minimum angle of rotation. How do we do that? It's actually pretty easy. You see, if I were to connect the center, I don't know why I'm even trying to dash that line. If I were to connect the center of rotation with each vertex on this pentagon, with each vertex on this pentagon, right, then what I can really see is that that is the minimum amount of rotation. But how much is that? Well, that minimum angle of rotation will be 360 degrees divided by how many angles make up that full rotation, and that's 5. And if I do 360 divided by 5, I get 72 degrees. But be careful, of course, because choice 1 isn't correct, right? Even though it says 72 degrees, that's an angle that does work. I'm looking for the one that wouldn't work. Now, if I was trying to rotate this point all the way over here, that would be 72 degrees times 2, and that would be 144 degrees. Again, choice 2 is wrong. We're looking for the angle that isn't correct. So then I might think about rotating it 3 of those, so 72 degrees times 3, and that would be 216 degrees. Now, I don't see that as a choice, so I am not too concerned about it. Let's do one more. If I do 72 degrees times 4, I would get 288 degrees. All those choices, 1, 2, and 4, are choices that do map the object onto itself. And in fact, I could do one more. I could do 72 degrees times 5, but then I would get 360 degrees. For every regular polygon, you will have as many angles of rotational symmetries as you do sides. In other words, right, for this regular pentagon, we have 72 degrees, 144 degrees, 216 degrees, 288 degrees, and 360 degrees. 5 different non-trivial angles of rotation about that center point. The one that doesn't work is 224 degrees. That would put us somewhere between 3 and 4 of those basic angles of rotation. All right, so what was our right choice? Oh, choice 3. All right, let's keep going. Let's analyze the symmetry of one more figure. Okay, here we go, a little bit more complicated. This one's kind of fun. Let's take a look at exercise number 7. The non-rectangle parallelogram, because rectangles are parallelograms, the non-rectangle parallelogram ABCD with 4 equal sides is shown below, known as a rhombus. The diagonals of ABCD are perpendicular and meet at M. Explain why a counterclockwise rotation of 90 degrees about M will not map the figure onto itself. So one of the really kind of cool, remarkable things that we'll study with rhombi or rhombuses is that their diagonals are perpendicular to each other. So the question is, why can't I take this figure, rotate it 90 degrees about point M, and have it land on itself and have it be a symmetry? Take a moment, use tracing paper if you need to, and try to write down an explanation for why this is true. All right, let's talk about it, okay? And you can really, really see this with tracing paper. If I've put my tracing paper up there and I rotate this by 90 degrees, look what happens. Cool picture. You know, it's like one of those ninja throwing stars or something. Not the point. The point here is that obviously it didn't carry the figure onto itself. A 180 degree rotation would have, but this 90 degree rotation again doesn't get the job done. And the explanation is pretty simple. It's because, right, I would say it's because the length of diagonal BD, right, this diagonal, is not equal to the length of AC, right? Because those two diagonals don't have the same length, if you will, then when I rotate 90 degrees, this line segment, MB, ends up coming up here and missing A altogether, right? It doesn't hit vertex A. It doesn't get mapped onto itself. Side note, the reason that I had to throw in the fact that it was a non-rectangle, although that's pretty obvious from the figure, is that a rhombus that's also a rectangle, known as a square, would have 90-degree rotational symmetry. So if we had a square, all right, then when I rotated it 90 degrees about its center point, that would get the job done. It would map the figure onto itself. All right, so let's wrap this lesson up. Symmetries. Symmetries are the last type of transformation that we're looking at for right now. We'll come back to them later. We'll take a little bit of a hiatus for a few units. Whew. But symmetries are the last type of transformation we're looking at, and they're a very special kind. They're any transformation that takes an object, a pre-image, and maps it right onto itself. So after you've done the transformation and you look at the object, it looks identical to the way it started, both in its physical location, its size, its shape, everything. What we see is that symmetries have to be rigid body motions, and they're almost always either reflections or rotations. I'll leave it to other courses to explain why, on very rare circumstances, translations can also be symmetries. But in that case, you have to have an infinite tiling of the plane, and that just gets into some deep stuff that we're not going with right now. All right, I want to thank you for joining me for another Common Core geometry lesson by eMATHinstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.